Okay, today we want to walk through a bit of an end-to-end overview of our service, the IBM SQL Query. So this is supposed to be a complete introduction end-to-end. So to motivate what we're doing here, one way to look at it is to just compare it with other kind of industries or principles that everybody is aware of, like about mobility. If you think of mobility, especially individual mobility with cars, centuries ago, decades ago, maybe a century ago, of course there were cars, but a lot of car owners didn't just own their own cars, they even had a driver basically just for them, right? Later became more common that you had your own car and you're driving your own car. But in order to be very flexible, especially, for instance, if you're traveling, if you need to be ad hoc in certain places, well, you just rent a car. And nowadays, what happened over the past years is that these car services, these car sharing services came up, like Uber, Lyft, and Co. So very, very flexible and ad hoc, and you really are not interested in the car as such anymore. And it's also less of a prestige thing more, right? So what matters is you can basically get from A to B. And if you take this principle, that's something that we also see more and more in the IT, and also even maybe more specifically in data and analytics. So for the area of big data, there have been for a long time very specialized systems, and they are still there, for enterprise data warehouse that are really optimized for storing large volumes of big data and processing and analyzing it. And they are highly integrated and sometimes even coming together with hardware as an appliance. So that's a form factor that is very well established, but nevertheless, some 15, 20 years ago, Hadoop came up and became very successful, even though there were already enterprise data warehouses. Why? Because they introduced more openness. Openness in terms of deployment options, hardware that could be used to run it on, cheap hardware, heterogeneous hardware, but also openness in terms of the data that can be processed, data formats. It's basically you can bring your own data formats, and Hadoop can just read and write those data formats. And also openness to the types of analytics that you can run. It's not just the SQL-oriented processing. There are various other libraries and algorithms that can be processed with Hadoop. So that was a big step forward, and we see ourselves today now at a similar inflection point when you look at how does the qualities and the benefits of cloud actually apply to big data processing. How basically you can get this seamless elasticity, this complete ad hocness and pay-as-you-go consumption available for big data processing. And also, if you think of cloud solutions, they are typically pretty disaggregated in terms of services and microservices that are composed pretty flexibly and that are by themselves pretty standalone. So we can see this also for big data, that for instance on the storage side we have object storage as a very cloud native, highly resilient, extremely durable, extremely scalable, and also extremely affordable storage option in the cloud. And this data persistency is now becoming eligible and available for big data processing by having other services that you can combine with them, for instance to do SQL processing. So that's actually the area that we are now, and that's what we are looking at. The following is basically representing exactly this kind of evolution here as a state-of-the-art cloud-native big data analytics stack. Now, one evidence that you can see is if you look at what analysts are tracking here, it's quite interesting to see that things like SQL on object storage is something that is on the Gartner hype cycle, for instance, for a while already. So this is from last year, 2018, where it's already tracked as basically just has passed the peak of inflated expectations, but it has been on this chart already the year before. So this is really a trend that is something important in the big data industry. And many vendors actually are investing and providing capabilities in this area. Now, serverless. So we just already mentioned it in one of the previous slides as a keyword and a consumption model that many people talk about today. And what it actually means to use serverless consumption models and form factors is basically, this is for IT industry what gives you a sharing economy, right? So you basically, serverless is the most powerful mechanism to really enable IT resource sharing. And this also applies to analytic systems. So traditional analytic systems basically had a rather fixed capacity, right? Especially if you think of appliances, this is a pretty fixed set of resources, and it's a very big effort. Maybe sometimes even have to, in order to increase resources, you maybe have to replace the entire system and completely migrate your data to a new system. And it also often involves specialized teams who are basically there to really manage certain aspects. Special teams who basically are only there to manage the data model of your system. Other teams that are there especially manage data ETL, how does data get in and out of your system. And then you have basically analysts, analytic users like BI users or data scientists, who only basically access very special curated data that others have prepared for them in an enterprise data warehouse. And this is not really flying well anymore with what you need today in a highly agile, innovative enterprise, where you have a very wide range of teams that basically you want to give access to insights, to data, and then insights, or enable them to produce insights at all kinds of stages of a data pipeline, right? Very early on when the data arrives already into your systems, you want to enable teams to work on that, or also later basically in the cycle when it has already been curated and prepared a little bit. So you want to be very flexible to enable them to basically engage at various stages of your data pipeline to derive basically insights from that data. And you want to enable data engineers to be very self-service to do all that and not have to basically negotiate and wait and plan before they really can start working on the data and then basically implement big processes before something is working. So they need to be very ad hoc and self-service. And of course, it needs to be highly scalable to really realize benefits of a cloud-like architecture, because a lot of data today is also coming in a very highly volatile way, also in terms of data volume, the types of data. So all of that basically needs to be pretty adaptive in a self-service fashion. Now, let's, in the following, review a little bit the key, let's say, ingredients of such an analytic sharing economy that we need in our stack in order to really realize this vision. And we're starting at the bottom with the serverless storage. Serverless storage, I have already mentioned, object storage in this context. That's what we're now talking about. So what is object storage? Object storage is basically something that gives you just a very high-level organizational abstraction of your data. So you have the concept of buckets, and in these buckets you have objects. So that's actually the only organization unit that really basically is exposed by object storages. It's pretty, and these objects are in a flat name hierarchy, in a flat namespace. So there's not a lot of sophistication in terms of the organization of the data. It's pretty straightforward and simple also. Also the access, it's entirely REST-based, right? You always just do gets and puts to basically read and write data. All the data is encrypted, be it on the wire, but also when it is stored. That's what all object storages have in common. And it's very elastic. So from the user, basically, it's completely elastic, right? It doesn't basically plan ahead in terms of how much gigabytes do I need. It just comes with the data and in your bucket, and you just throw data at it, and it grows and shrinks as you go. And it's highly affordable, pennies per gigabyte. It's really like that. It's just a few cents for storing a gigabyte per month. And it's highly durable. So you're completely relying on it. Basically, the data is safely stored there when you have it there. Now, IBM obviously is one of the players here with object storage, and our technology is based on CleverSafe. It's basically an acquisition IBM has done a few years ago. So what is especially basically distinguishing on the IBM Cloud Object Storage? One is the high degree of flexibility for different types of resiliencies. So you can basically store data just within a single region, or you can also store it cross-region, and that's really just a configuration option. There's nothing that you have to set up. You just say, I want this data to be stored cross-regional, which means it's automatically enabled for disaster recovery out of the box. Right? If an entire region burns down, these data are still available, you can continue to read and write it. And it has various different storage classes in terms of temperature of data that is more frequently read, you can put into the standard storage class. Data that is just read very infrequently can put into cheaper storage classes, where the read and the access then might cost you a little bit more. IBM Cloud Object Storage, like actually most object storages, is S3 compatible. So you have solutions that are built on AWS S3. You can also run them against the object storage because it's 100% API compatible. And we have user-managed encryption keys, so you can, with IBM Key Protect, basically the user can control the keys that are used to encrypt the data there. Now, one of the qualities that we have is this data is enabled for SQL queries. That's one of the things that we are diving into later today. So it's not just cold storage, it's really storage that can be used for data transformation and analytics. And we have integrated a very convenient way to efficiently upload data into the Cloud Object Storage with Aspera. So that's completely embedded in the stack, in the tools, in the UI, and in the SDKs. So that's something that you do not have to set up yourself just to use it. So that's IBM Cloud Object Storage at a glance. And that's the basis for this whole sharing economy of analytics, because this is our persistency of this analytics data. Now, let's look at how do we get data in. Data ingest into this stack, basically into the Cloud Object Storage. So we can focus maybe on 2 dimensions. There might be more, but for now, let's look at 2 dimensions here. One is how much serverless is the ingest options? What's the degree of serverlessness? And how basically flexible is an option versus it's just working out of the box with a push button. The most straightforward thing that you can use is the IBM Event Streams, which is IBM's Kafka as a service. It's basically really just pretty much Kafka with topics and message queues that is available as a managed service in the IBM Cloud, and there's a straightforward connector, so-called Cloud Object Storage bridge that you can configure in order to pretty much land the messages that come in more or less directly in Cloud Object Storage. Just write in the Cloud Object Storage as they arrive. There is a kind of serverless option available in the IBM Cloud that basically where you're just paying by the number of messages processed. So it's rather serverless in terms of the consumption. A slightly more sophisticated way to process message data before you're writing it to Cloud Object Storage is IBM Streaming Analytics. It's IBM Streams as a service. That's something which is not really serverless at this point. It's basically a dedicated instance that you have to provision and basically pay also by the, I think by the hour or by the month. in order to process message data, but it gives you much more sophistication in terms of pre-processing and for instance, batching up of messages before you're writing them out as a block to Cloud Object Storage. Then we also have IBM Cloud Functions, which is also an option you can use to ingest data to Cloud Object Storage, because you can trigger Cloud Functions message by message that are coming in from a Kafka topic. And then you can have completely, basically, custom way to process the data, use custom algorithms, custom transformations before you write them to Cloud Object Storage. So obviously Cloud Functions does also have simple ways to connect to Cloud Object Storage, but it gives you the complete custom coding capability that you can inject as part of the message processing before you land it. And it's of course, as our serverless technology for function as a service, entirely serverless in IBM Cloud. And finally, must not forget, there's also Aspera, which is basically not really a service that is active for you. This is something that you can call. The other things are basically triggered by the event, by messages. With Aspera, you can just upload data completely driven by your application. So you would have to drive that, right? So if you have data somewhere, you can use via the COS SDK Aspera under the hood in order to write data to Cloud Object Storage in a pretty custom way. So these are just the ecosystem of ingest options that basically you should be aware of. How do I get data actually into this Cloud Object Storage? Next, we want to look at the data processing and also a little bit of the analytics there. So this is something which is not 100% two separate things, even though there are two separate problems. One is how do I transform and prepare data, and how do I conduct analytics. But as you will see, we have actually a service eventually that can do both. So that's why there's a little bit of a dotted box here. But let's first focus on the data transformation, and the service that we are using here is called IBM SQL Query, which is targeting developers, but also other users, depending on their degree of sophistication that they have in terms of writing SQL. We address them either directly, like data engineers or data analysts, or indirectly through some tooling layer that is in between and generates SQL. So important to understand is this service does two things, two major use cases: data transformation and analytics. And it does so on data in the cloud. So what does it mean, data in the cloud? Primarily it means Cloud Object Storage, but what is definitely within the scope and the charter of this service is also other cloud data sources that we can read and write to and from those other cloud repositories. And it does so in a serverless fashion. So what does it mean to do it in a serverless fashion? Well, what are the effects of doing that? First of all, it means it's 100% self-service. The users of that do not have to set up anything. They can just come and start using it. When they have data in one of on Cloud Object Storage, they can just start writing SQLs against that. And it's entirely enabled via an API. Everything you can do through an API. It's highly affordable, and it's basically a charging model by the data that is scanned per query. Cost is $5 for a terabyte scanned, which is basically exactly looking up the competitive landscape that has the same kind of pricing for this type of SQL service in the cloud. It is very well suited for machine-generated data. What does it mean? Well, it means that machine-generated data is, first of all, very elastic. I mean, there can be a lot of data being produced. You cannot actually foresee and plan ahead necessarily how much of the data is coming in at what point of time. So this basically serverlessness accounts for that, basically to just grow and scale your query processing together with the data as it is coming in. The other thing is machine-generated data is pretty diverse in terms of formats, also in terms of schema structure, basically. So there's a lot of evolution that you have to be prepared for, that the data, there might be new properties suddenly coming in. So this service also accounts for that and basically can really go from, without very little assumption only about the data, it can go from the data. So the only assumption that is made, it needs to be one of the supported formats of open data structured data formats like CSV, Parquet, ORC, and so on. But we don't assume a certain schema, for instance, right? So we infer the schema with this service when the query is run. And with that, it's also very good for ad hoc data exploration. So especially if you don't know anything about the data yet, right? You just have done the ingest of your messages, but you basically don't have the idea yet what are these messages it's actually containing, and maybe what are new messages from last week containing. Is it something new? You can use this service just to start exploring your data. Right? It just can do that to say, okay, I don't know anything about the schema yet. Just let's look into this, give me a sample, and then go from there and prepare your further steps after you have done this data exploration. Through the power of SQL, the SQL engine that is included here, it is really also very well suited to do all kind of data transformations. Right? It can use the full power of SQL to do data transformations, plus a couple of other things that we're going to look at later that help you to really also decide about data format changes. Not just data content changes, but also data format changes and layout changes. And it is very well suited also to operationalize those pipelines that you have. You have basically explored the data, then you have decided for some data transformations, and then now how can you operationalize it and automate that? It's basically very easy to do it with a service because A, it has the API, and B, it integrates with other frameworks that I'm going to look at later at the end of the presentation that help you to automate these kind of things pretty nicely. So it's not just very ad hoc and flexible, it's also scaling out on demand by the job, by the query. And why? Well, because it is internally running on Apache Spark, which is a pretty flexible and powerful scale-out framework to basically scale out single jobs to massive number of basically cores and across multiple machines. Well, and what can you do with that? Well, you can, for instance, build data lakes for big data. So we can call them big data lakes. So that's something where this is just a perfect tool to do that. And eventually, it enables you to do analytics directly on object storage without a database or data warehouse involved. Now, we want to look briefly at the architecture of that one and how does it all play together. Well, at the center, we have our persistency, the IBM Cloud Object Storage, with some data that sits there. Now, how does the data get there? We have already reviewed the different ingest options. You might have already data in some other systems, so you want to maybe export and archive it there, or you use it as a primary landing spot of data at all, so not stored anywhere else, just directly landed in Cloud Object Storage, or you have it in some other systems, maybe an on-prem system, and you can use Aspera to upload it there. The service is a batch service at the core, which means the following. The application just submits a SQL. The SQL is then processed by the service dynamically. It decides what data needs to be read. It reads it into the Spark engine. In parallel, it does a scale-out processing of it and writes the result again to Cloud Object Storage. So that's the core of the service. And the result itself, it depends on what the application wants to do. It may read it back, right? So if that's the purpose, if it wants to produce a result that it wants to consume right away, but if you think of data pipeline processing, it might just basically just submit the next SQL afterwards to then just read the result and do the next step with it. So it doesn't necessarily mean it always has to read the result into the application. Now, so this is at the core employing the full power of Spark, but there's a couple of basically IBM IP that is flowing in terms of the capabilities of processed data. One is that we have a geospatial library that implements the full geospatial SQL standard, sometimes also known as PostGIS, that many other databases, data warehouses today already have. We have the full implementation for that, and it's pretty, actually a state-of-the-art implementation, pretty sophisticated. And we also have Timeseries SQL, which is really something brand new in terms of something that's available in the form factor of a SQL engine. So there's no really complete Timeseries SQL database today. What we've implemented here goes pretty far in terms of the breadth of time series calculations. Going to look at this later in the presentation. And we also have a beta running for data skipping, which is also the first in the industry of a serverless SQL service that can do indexing of data on cloud object storage and consuming these indexes when the query is run and executed to optimize I/O, right? To know basically exactly the objects and basically can contain candidate data based on the predicates of the query. So that's the basic fundamental architecture of the service. Now, if you look at this application here at the top, what kind of applications, what kind of interaction models are possible with the service? So, first of all, there's on the top here this create experience where we have the SQL Web Console. That's getting started, and the experience that pretty much every user will probably go through. It's not just meant as a getting started, it's also meant to be the creation experience for SQLs. So it's basically the IDE, the development environment, to test and author your SQL statements before you basically then operationalize them in some other way. One way to basically then take it further is to put it into an interactive data analysis and visualization experience, which is Watson Studio. So with Watson Studio, you can create notebooks, and in notebooks you can also use SQL Query through an according client SDK that we have available, and that allows you to run SQLs and do anything with the results in terms of applying other machine learning algorithms or just putting it into visualization in a pretty flexible, interactive way to help data analysts and data scientists to work with the results of the SQL query. A more unattended way to basically operationalize the SQLs is to deploy them as Cloud Functions, which means you have a SQL statement now being an executable asset that you have stored, basically or deployed in the IBM Cloud, that can be run either by invoking a REST endpoint, or that can be just automated by cron jobs or events that trigger this Cloud Function. At the heart of it, basically, it's all driven or it's all implemented through an API. So there's this REST API that you can either use directly from any kind of application, integrated into any kind of solution, or use it through some of the SDKs that we have made available, Python, Node, and we also have a JDBC driver now as a beta. Okay, now let's this is more to introduce the service as a whole, and as I already mentioned, it basically does these two major use cases, right? Remember the transformation and the analytics piece. For transformation, one of the key things why you want to transform data is in order to prepare the data to make it query friendly. And that's very important, and it's the key to success for any kind of analytics that you want to run on cloud object storage data. You basically should take care that the data is laid out in a proper way so that the analytics can run in an optimized way. Mostly what you want to optimize is really I/O. You want to basically, because we are talking about this disaggregated architecture, so storage is something else than the actual analytics engine, and there's a network in between those, so it makes a lot of sense to minimize the I/O between both. And you do this by laying out the data. And to minimize the number of requests that need to be run to read data into the analytics, and to also minimize the overall number of bytes that need to be read. And there are various best practices, and there's this link here on the basically in whole blog article that we've released that show you how to basically lay this out. For instance, you take care about a sweet spot of object size, so which turns out to be 128 megabytes, which doesn't mean that basically it gradually gets worse when you just have 100 megabyte. But there are certain points when it falls apart. For instance, especially when you have too small objects, so you shouldn't have kilobyte-sized objects. So that's something that you should take care of. You should also use a good format of the data that allows you to, for instance, compress the data, but also gives our engine much more insights in terms of the data structure. And there are various options that we are going to look at later. And you should lay out the data in a proper way in terms of partitioning it. And there are also many different options that you can use here. One thing is also in general, even though we do support that, it might be an immediate cheap idea to say, oh, I want to compress my data so I have less I/O. Yes, sounds nice with gzip. So you can, especially for text data, CSV, just nicely compress it with gzip. But actually, that's not the right compression that we recommend as a best practice. Actually, it's the worst that you can do in terms of performance, because gzipping it means we have to uncompress everything before we can do anything in order to skip I/O in the data itself. Now, which formats? I already mentioned it. Format matters, and you can see on the left side, gzip is basically the worst one that we recommend. Then we have textual formats like CSV and JSON that we just support, and they are nice, have a nice, basically well-known structure that we can go from, but not a lot of, let's say, metadata, right? It's just text data. And we have to infer, for instance, the data types by really looking at the values. So this is costly to do it, but it works. And then there are more basically sophisticated formats like Avro, ORC, and Parquet. And especially ORC and Parquet are basically recommended because they are columnar-oriented, which means the data is stored column-wise in the individual objects of those formats, which gives us a lot of structure in those objects to say, I only need the following columns to read, for instance. So we don't have to read the full object if we just want to select column A, B, C. So the optimum that we recommend is Parquet, which, as I said, is one of these columnar formats and allows us to read only the columns that are really needed. And due to the columnar format, it also gives us a lot of compression options, right? So because you can run length encoding of data, so that's just the best in terms of compressing large volumes of data. And there are other metadata that is stored in the Parquet, like, for instance, the min and max value per object for the columns. You should combine it with layouting, and there's a best practice. It's called Hive-style partitioning that has evolved over the years in Hadoop ecosystem, that we just support exactly in the same way on Cloud Object Storage, which means the file name, or in our case the object name, includes a naming convention for certain basically grouping of values of the data. So basically this is then, so to speak, the partitioning key that have been used here, like in this example on the screen, the date time column, the DT column, is used as a partitioning key, and each object basically just contains data from one of those date values. And that's now something, that's a structure, this naming convention, that's exploited by us when we run a query in order to figure out which objects we have to read at all, if there's, for instance, a filter set on date time. Now, how do basically the user of SQL Query address this data? So that's one of the key things. After all, it's just SQL, but one of the things that is specific to the service is the table locators, because a table for us is just data or data set on Cloud Object Storage. So how do you address this? Well, through a URL format. It starts with COS, it stands for Cloud Object Storage, and then you come up with the endpoint, which is basically pointing to the service endpoint in the IBM Cloud for Cloud Object Storage. The bucket name, as I said, this is the logical grouping of data in Cloud Object Storage, and within buckets, the so-called prefix. A prefix is like basically a qualifier of one or more objects. So depending how detailed you type up or you specify the prefix, it may qualify just for one individual object, like in this case you can see here, this parquet, so this is really meant to be just this one parquet file / object to be read, but you can also treat it in sort of a folder manner here where you say everything that starts with my data is now qualifying. Or maybe here, everything in this bucket at the bottom. All the objects in this bucket. And we treat them just as partitions of the table. So that's basically the basic locator format. Now, there are various different things that you basically, in addition to the URL, that you can specify. One is the table format. We can say, okay, which format is it stored in? Is it CSV, Parquet, JSON, or the other formats? And depending on the format, you can also tell us, well, maybe my fields in the CSV case are using a non-default delimiter and these kind of things. And you can also specify this job prefix thing, which means when you're writing data, so this is more for the target, basically, we will not generate a unique prefix to identify the result. So you can specify, I want exactly this location to be written, and no additional prefixes to be added. The table partitioning is another component that you can append here. Basically, that says, I want my data to be partitioned in the following way. For instance, if you just specify partition by, that means you are producing hive-style partitioning. And that's something that's quite important because I've explained that this best practice matters a lot. Now, how do you produce this best practice if you just have pretty data that is not adhering to this best practices? How do I get there? Well, it's just the matter of adding this clause to your SQL in order to produce best practice data layout. So it's something very approachable and very easy to do. There are other forms of partitioning that you can use for other reasons. For instance, if you want to optimize for the number of objects being produced, then you can use this into clause. Or if you want to basically have objects that all have the same number of columns, you can use this every clause, which means that's something very useful in the case of pagination, right? The application wants to run a SQL, and then it wants to consume the results, maybe to let the user step through the results in a UI where he just presses next. Well, that's a very elegant way to achieve the pagination by just running the query with every clause. And finally, you can combine it also with the sort by clause. It means you can cluster the data. So I can say, I want to create maybe 10 objects, but I want my result rows basically be sorted across those 10 objects by the following list of columns. So as you can see, there are very sophisticated ways to lay out your data, but just by using these syntax clauses in a simple serverless SQL statement that you can submit. Now, under the hood, as I told you, it's the REST API, so let's just take a brief look how it looks like. It's a pretty straightforward REST API with 3 major endpoints. So the post endpoint that you can see here, this is used if you want to submit a new SQL. And when the return of this post call is basically a job ID that you then can use in order to check the status of this job, whether it's still running, and when it has finished, where can I find the results of the SQL. That's then the next endpoint. It's this get endpoint, where you just append this job ID here into the URL. And finally, there's also this list endpoint that lists to all of the recent job executions. So that's basically it. So that's all what we need in order to basically serve all of these capabilities, because a lot of the capabilities are actually made available through SQL syntax. Like you've seen all of these transformation capabilities. It's nothing that the API really supports explicitly. It's something that the SQL syntax supports. Now let's look a little bit more at the things that are more important for the analytics part I already mentioned, as I said, it's one service that basically, depending how you use it, you can just transform data, or you really produce some analytic results that you want to consume. So what are the things that are especially useful for analytics? Well, one thing is, it's all Spark, right? So everything you can do with Spark and Spark SQL specifically, you can do with the service. For that reason, we have this Spark SQL reference that we have made available as part of our documentation, and it's actually the best Spark SQL reference that you can find in the market today. And it's interactive. You can basically really drill into the individual capabilities just by clicking on these boxes that you can see here on the screen. You have examples, SQLs for every single option, syntax option that we have, that you can just copy and paste to run in your SQL web UI to try out these examples. So it's pretty approachable, and it's a very nice way to learn Spark SQL. But as I mentioned, we definitely go in terms of the capability that you can do beyond what Spark SQL, the community, can do. So, and one of the really cool things that we've added is this time series library. This is really something that it treats time-stamped data as a first-class citizen. Basically, it's a column type. So time-stamped data means you have a series of measurements, for instance, with a timestamp, like a sensor feed, right? So where you have for each sensor, for each device ID, you have a sequence of, this is the timestamp, this was the measurement, this is the timestamp, this was the measurement. So that's one time series. And then you may have 1 million devices, so you have 1 million of those time series. Or you have more, not these numeric measurements, you may have categorical values like in the click stream, you may have a user session that has been basically where events have been sent every time the user clicked the button or you opened a new link. So it's basically just, again, a timestamp for the session within the session and a URL. So that's again a time series. So those are the examples of time series. Now, the challenge with handling time series is if you want to analyze those and derive insights from those, you typically want to basically, or you very often want to compare time series, right? So you want to group up time series and want to put them into the same bucket and do aggregated analysis on top of that. How can you do that? Well, you need to put different time series into lockstep. How can you basically have this measurement from this device to this measurement of that device and basically correlate or even join it if they have their complete own measurement cycle, right? There's no centralized clock on these two things. So they have completely different timestamps that are not exactly matching. That's something that this library just does with a very simple SQL function. You can just call and say, okay, correlate these time series and bring them in lockstep and, for instance, interpolate the values that maybe we're missing in one time series over the other in order to basically be able to join them together. Another way of using time series is that basically you want to basically put them into segments. You say, okay, I have a time series over a full week of these IoT measurements. Now I want to look at hourly aggregates, right? And it's again just a simple function call that runs this segmentation on all of your time series at once. Then you want to use time series maybe to forecast, right? So you look at all of the measurements up to this point. Now let's try to predict, and let's do this for all of my 1 million devices at once. So you can use various algorithms, forecasting algorithms that are just built in. Or let's think of these click streams that I mentioned, like these sequences. So you may have figured out that a certain sequence of user actions basically leads to a purchase. Now you want to basically figure out all of the ongoing user sessions that I currently have in my and figure out which ones basically are good candidates to basically finish this transaction. So you want to basically look at those ones that have a certain sequence of events, and that's just a simple SQL to match to do this matching. So as I said, so this is really a very sophisticated and broad set of features for time series analytics, all available through the SQL syntax. In a similar way, I already mentioned earlier that we have also these geospatial extensions. This is something where there is actually standard defined for many years already as part of the SQL standard, so-called SQL multimedia standard, sometimes also referred to as PostGIS because it has been implemented in the Postgres very originally, and they called it this way. And it gives you a way to treat location data as a native data type. Location data is really, in the simplest case, just a point, like a GPS recording of a device at this point in time. It might be just longitude, latitude, like a car has been at this position. Can also be something more complex, like let's think of basically a whole GPS track, and it might be a line, so-called line string, or it can be something even more sophisticated, like a polygon that represents, let's say, a zip code area or something like that. And we can basically treat them all, and there are standard operations to do geospatial correlations, geospatial joins, geospatial aggregations, and so on. This is all standard, and we have implemented it, but we have implemented it with a very so-called full Earth system. While most of the databases out there that you find today have implemented PostGIS in a way that they are projecting data to a flat Earth model, so a two-dimensional, basically, system. All our computations are internally in our spatial library are really based on the round Earth projection, which means we have much more precision. We don't have these artifacts of projection, and especially if you're going to the poles, like think of oil drilling and these kind of things, where very often close to the poles, this matters a lot for precision. Now, let's put this a little bit into maybe an end-to-end scenario, how it plays together. So you may have a lot of sensor data coming in, right, from devices, from mobile devices or cars, basically automotive, and they're just sending data, measurements after measurements. And what we do now is first we just landing all of this data on Cloud Object Storage. And first we are basically using geospatial SQL constructs in order to filter data. Give me only the data that is within, let's say, Germany or within Stuttgart, a certain location that we are interested in to analyze now. It's a simple SQL where clause basically that we are applying. It basically filters by a certain geography, which is really a so-called polygon, like I mentioned already, that gives you the exact boundaries, and only those devices that were in this boundary are interested to us. Then we may want to basically sum up, aggregate up information from multiple devices within those in this area, from multiple measurements in this area. Now we're combining with time series, which means basically we do this basically across time, right? These aggregations across time. We don't aggregate everything that happened in this whole time frame, but now basically we do this device by device, stored as a time series. And then we may want to join it up with other time series data that we get from other devices, and we correlate time series data. So, which means this geospatial and time series data, this is a very nice combination, these capabilities, and that's why actually also these libraries that we have packaged up, we call them the Spatio-Temporal libraries, because they are very often used together. Another thing that matters for analytics a lot is optimizing the query performance. I've already elaborated that the basic art of doing that is by taking care of the data layout. Now, we are now going a step further here, is that even if you have laid out your data according to best practices, well, this might be very well suited for a certain set of queries, but not for other set of queries, right? And anyway, this hive-style partitioning and so that I mentioned, it has certain limitations in terms of the sophistication of partitioning that's possible. So it still means that it might not be ideal for all of your queries. For that reason, we have introduced this data skipping index now that allows you to index data after the fact, after it has been stored already and laid out in a certain way, to store metadata about the objects explicitly. like for instance, the min and max values for all of the column values for all of the objects, or the number of distinct values if you think of categorical data. Or if you think about location data, you can store so-called bounding box indexes, which means in this object, all the data that basically is in each object is in this bounding box on the basically coordinate system. Which means if you then come with a query, we can apply additional filtering of I/O. That's why we call it data skipping, before we actually really have to read the data. So it gives another order of magnitude of I/O optimization that is possible on top of already the optimized data partitioning that we have already applied, which means it saves two things. It saves time and money, right? Time in terms of the query performance, it's faster because we have to do less I/O. And since we are charging the user by the volume of I/O, also the query will be cheaper. And that's also something which is pretty unique. It's actually the only serverless SQL service that has its capabilities nowadays. Another aspect for analytics that is important is that a lot of analytic solutions and vendor tools today that work with data, they assume JDBC. Especially in the BI, business intelligence world, a lot of data, BI tools, they just access data through JDBC and ODBC drivers and databases. Now, obviously, we are not a database, but of course, we can participate in this ecosystem by exposing this JDBC interface. So we have done this now with the JDBC driver that we've built, which is only in beta at this point. But basically what it is, it's an entire wrapper of SQL Query REST API, exposing and emulating a full JDBC protocol on top of that. And we have worked with Looker as one of our sponsor partners to make this available. This looks like this basically, that here we have example Looker dashboard basically that really uses a data directly in Cloud Object Storage without a database in between, just by using our JDBC driver and running SQL statements against Cloud Object Storage. Now, so this is basically a couple of aspects that are important if you think about how do I build analytics on top of this data after I already have prepared the data. Now, when you've done all that, you have really cool, you have a lot of data preparation that you've worked out to optimize the data to a certain layout. Now you have created your analytic queries, all good. How do you automate all that? How do you automate all of these processings and pipelines and even analytic queries that might produce a report or things like that, or results for a report? How do you automate all of this? The key for that is Cloud Functions. Because Cloud Functions is just a perfect match because it's also serverless. And in fact, many people, when they think of serverless and IBM Cloud, they first think of this, not yet of SQL Query. So what is Cloud Functions? Well, Cloud Functions is function as a service that allows you to run custom code that you have coded up as a function on demand, right? And you only pay for the execution of the function. That's all what you're paying for. So that's why it's entirely fair. If there's no workload, you don't pay anything. You don't pay for idle. It's highly elastic that way. So basically, you can start with the function executions once in a while, or you can basically also run 100 function executions in parallel. Just basically it will handle for you this burst, so to speak. It's polyglot, which means you can use very different languages, many different languages to write up your function. And in fact, now also SQL as a language, because we have a default SQL Query Cloud Function you can just instantiate, where all what you have to specify is a SQL statement that it should run. And it's based on open source. So it's OpenWhisk, that is the open source here. But the key aspect that I want to focus on here for this section is this automation, which means if you have a Cloud Function, whatever way you have created it or written it and so on, what you can do with it is you can automate its execution. in various ways. You can have triggers that are basically firing at certain events. Or you can also have schedules, which is basically just a special form of a trigger, because you basically specify, it's like a cron schedule, whenever the function should be executed, and then it runs it for you. And you can orchestrate functions into sequences. So you can basically build compound functions by combining 3, 4, whatever other function executions in a sequence. And then basically you can treat this whole sequence again with a trigger, with a schedule, and so on. And this is the key to build data pipelines if you think of individual functions now being SQL statements that they run. Now, with that, basically, we can really look at the serverless stack for data analytics solutions. At the core of it, we have serverless storage, it's cloud object storage. We have serverless runtimes, it's cloud functions, and we are now adding into this the third major component, which is serverless analytics. That's the role of the SQL Query statement, SQL Query service here. And those three things together are really the core of a serverless data analytics platform. Now, let's look at some use cases, how basically really cloud functions really add clear value on top of already using a basic SQL query capability. One is, you can use it to get access to data that SQL Query cannot understand out of the box. What if you have data that is in a proprietary format? What if you have data that is in a sort of a binary, unstructured data format? Because cloud functions can run custom code, well, you have now a serverless option to run any kind of pre-processing, let's say a feature extraction, for instance, let's say face recognition. You have an image, you run basically a function that does a simple face recognition on this image and spits out just the name of the user. Oops, how did I get here? Sorry. That's one way to use combine cloud functions with SQL Query, also sort of in a pipeline manner, right? In a sequence. Next thing is, well, you can use cloud functions to automate running of SQL queries, because you can deploy a SQL statement as a cloud function. Once you've developed it, now you deploy it, and then use all of this triggering and scheduling, and also to automate its execution. Another thing you can use cloud functions as a sort of a stored procedure, if you compare it with database terms. Stored procedures means you have coded up one or more SQL statements that do a certain thing, it produces a certain result, and access certain data with certain predicates, or certain where clauses whatsoever. And then you have a result after running this. Now, what you can do now is, you can basically say, I'm not giving my users access to my data in cloud object storage. All what I'm giving them access to is run this cloud function. So you can shield the raw data from the end users by just giving them access to cloud functions and only giving them access to the processed data. So they basically, that's a way to sort of achieve more fine granular access control on your cloud object storage. And finally, yes, you can use the sequencing capabilities that I mentioned, really build entire pipelines of processing steps. Okay, so I hope that makes it clear why Cloud Functions is just such a perfect match for this SQL Query capability. Now, okay, so we have walked through these major ingredients of the serverless data analytics stack. What is it all good for? What can I use it for, right, more specifically? Well, first of all, it helps to understand that it's for data in the cloud, and especially data that is produced by the cloud. And sort of, if you think of cloud solutions, data is really in itself a very important aspect to really be successful running cloud solutions. Because understanding your own cloud solution, what it's doing, is really key to success. Your competitive advantage is if you really can react in a very agile way to the needs of your market, to the needs of your users, also to what your users are doing and what they're also maybe failing to do. So collecting this data is very important. Right? Collecting this data is very important, but not just collecting it, also analyzing it. So basically, you should basically be able to have a very flexible way that is just as flexible and as elastic as your own cloud solution. You should be flexible and elastic to monitor and analyze the behavior of your cloud solution. And basically what we are talking about is now log data. Right? So this log data of your cloud solution is a very important set of data that you need to get a handle on. This log data is also something that is very, very elastic and volatile in terms of volume. Right? So because depending on what your users are doing, how much traffic you get a lot of data or less of data. Hopefully over time you just have a lot of growth of this data. And whatever you're doing with this data, it needs to grow with it. Right? So you need to be as elastic as your own solution. You need basically be able to handle this data. So this is one area where this service, the stack that we just looked at, comes in very handy, right? Application log data. Let's look at it more specifically. A special type of log data is clickstream data. Clickstream data is data of user behavior and user interactions with your solution in the cloud. And what kind of examples of basically important insights you may want to get out with clickstream data. One is basically what are so-called friction points in your digital journey. The digital journey is really the journey of the user as he basically goes through your solution, right? Also maybe across multiple days, multiple sessions. You want to really monitor this user basically what he's doing. And for instance, how many clicks does it need for the user to get to a purchase? What pages did he visit many times, even though they are not meant to do that? Like, for instance, you may have entering payment details. If you see that a certain user is really going there 3-4 times, and if that's a typical pattern, maybe you have a problem because that's not what's supposed to do. Maybe he has just problems entering the payment details. Maybe it makes it complicated or things like that. What is the last page visited in a session? Where basically you can see, is it something where maybe this pisses off my users, I'm scaring them away? So this is really important information that you should basically understand in order to optimize your business at the end. Right? It's about optimizing your own business. What are the successful sequences of pages that lead to a purchase at the end? And if you have learned that, then basically you can guide the users to exactly the sequence, right? So to increase the likelihood that they are buying something with you. And on the other side, what are basically sequences that lead to churn of the user? The user leaving our platform, not coming back, or basically canceling their subscription or whatsoever. So that's something where you can see, okay, here you can really act. Same on what is likely page visits and sequences that lead to expansion. So for instance, the user looking at maybe different plans. What different plans does the server have? This might be an indicator for you to say, oh, maybe I should reach out to this guy. Maybe he's thinking of expanding his business with us. Right? So there are many different ways, a lot of business money actually hidden in the data that you can basically get. Okay. Now, and if you think of how do I manage this clickstream data, how do I get a handle on, you will see the things that you will need are pretty close to what we've walked through beforehand, right? So you need very elastic pipelines to process this data, to store this data, to prepare this data, and then finally to run analysis. And of course, you do not want to do this manually. This is something that you want to work out once, and then it should run automatically, and you should just get your report or maybe even a notification proactively if there's some important action coming up. The user, for instance, is about to leave. Maybe you just trigger somebody in CRM to basically automatically take a look after this guy. And it should be for your teams to be pretty self-service to build all that, right? So just as your cloud solution needs to be very agile in terms of the users, your developers to build that, also this second layer of analysis needs to be pretty self-service to be built. Okay, and basically at the end, it should be very flexible, and you need a pretty simple language to interact with this data, and that's actually pointing to SQL. Right? So it's a declarative way to interact with data and define all of these processing and analytics steps. Now, a typical way that you can see what is being built here, so this is more of an end-to-end picture of a scenario, is that this data basically coming into the cloud object storage through one of these mechanisms, be it application logs here, like this, the applications, they have just logging being dumped to cloud object storage, or in a similar way, we can look at these IoT scenarios. They're all storing this raw data on cloud object storage. As I mentioned earlier, the first thing that you want to do is you explore the data. Right? We may not have any knowledge, we don't assume anything, just go and explore the data. Before you start, now you build your pipeline. Okay, first I cleanse my data, basically get rid of noise, get rid of things that I have null values or things like that. Then I'm filtering for the interesting aspects, right? I'm only looking at data from, let's say, a certain region that I want to optimize or want to analyze. Then I'm merging it with master data. Think of IoT devices. The devices might just have IDs. You don't know what devices they are, what kind of devices, where are they located, and so on. So you may want to join with master data, with dimensional data, so to speak. You may want to aggregate it up to create hourly sums, daily sums, whatsoever. And then you may want to compress what you have then into a very high quality condensed data set, and really as something that is then the best base for analytics. So this would be then this compression into Parquet, for instance, right? While you might have started with JSON, at the end you have Parquet, highly optimized and much smaller also in volume. So that gives you a chance to really do direct analytics, like with Looker through this JDBC driver, or like with Watson Studio in notebooks, right? You can really directly analyze this data. But it only goes as far as basically you may have a certain expectation of latencies. There are definitely use cases where you have the highly interactive dashboards where basically, even though we have optimized it perfectly already, it's still a few seconds turnaround time to run a certain query. That might not always meet the needs. That's why there's definitely this place and use case where we are talking about promoting this data into a specialized database system, data warehouses, or other relational database systems in the cloud, and then only connecting those systems directly with a BI stack, for instance. So we always basically serve those two paths. For certain analytic use cases, you can directly go there, but for high-end, low latency analytics, we definitely basically also are going to promote this data and store it into relational database systems. So one of the scenarios, basically, let me skip that for today. I think we also talked about Clickstream. Because I want to take at the end a little bit end with the broader context that we are positioning this whole thing for. What we are actually building here is the foundation of a data lake that is cloud native. Now, data lakes is something that many people already know from Hadoop systems, and they have certain ingredients like HDFS for persistency, and then several engines for doing different types of processing, like Pig and so on for data transformation, and then maybe Hive for analytics and so on. And then you can also use more low-level infrastructure APIs like MapReduce to process any kind of data, also unstructured data. So there are a lot of components there, and what we are talking about here is establishing an ecosystem where you can do this in a cloud-native fashion without just hosting more or less monolithic Hadoop cluster in VMs, because that's not really something that is the best fit for a cloud. So we're talking about having options for persistency to store the data, to get data in and out with the data ingest options. We're talking about processing data with SQL for structured data. And then we talk about Cloud Function-based processing for unstructured data. And then we talk about the data catalog that is available in the IBM Cloud with the knowledge catalog, and our Cloud Function orchestration automation to automate basically this entire analytics and processing in this data lake. So that's what I want to end with, because that's the basically overall goal. What we are basically marching towards is establish exactly this ecosystem, and we're actually already a good path along those lines. Now, that's what I've prepared for this session today. At the end, we have some further resources that you can look at videos. There are links to the SQL reference and so on, and our blog articles. And that's what I recommend everybody to get started with. In addition, of course, to just getting your hands on to SQL Query, because it's really as easy as provisioning the service, a free plan instance, and a few seconds later you can do all of that, what I've talked to you about. You can do this yourself. Okay, so thanks. That's my presentation for today.